11, Lesson 2 on natural base, the letter E. So we're continuing on with exponential functions, but this time we're looking at a special little letter in math, E, and it represents an irrational number. So E is to exponential functions. Sorry, E is to exponential functions, kind of like pi is to geometry. So E represents an irrational number, but a very important one, and as opposed to writing that number out, we show it using the letter E. All right, so what is E? Well, first of all, it's something that you're going to use a lot in calculus and see in sciences, especially in physics. Okay, sorry, so E is defined by this little expression right here. So if I do 1 plus the inverse to the nth power, and n just represents any number. So if you keep doing that for every single number, and as it approaches infinity, it's going to approach the magical number of E. Okay, it's a special ratio, just like pi is in geometry, pi dealing with the circumference, blah, blah, blah. So anyways, the number that we use is 2.7128. You don't have to memorize that number, but just know what that ratio is right there. Okay, so let's take a look at what we can do with E in a couple different patterns. So in terms of just simplifying expressions that contain E, treat it just like a regular variable, right? So if this was like x squared times x to the 6, when we multiply common bases, we add our exponents. So this ends up being e to the 8th. All right, when we divide, we can divide our coefficients and subtract our exponents, so I get 3e. When we have our outside exponent, just raise everything to the second power. So negative 4 squared is 16, e to the 3x squared, so then I just multiply those coefficients. Okay, so I'm just, using my basic exponent rules. Negative 7 plus 8 gives me e to the first, which is just e. Over here, I'm going to raise the outside exponent first, so negative 27, because negative 3 cubed is negative 27. E to the 12th over negative 9, e to the 7th. And now I can go ahead and divide my coefficients and subtract my exponents, which gives me 3e to the 5th. All right, so let's just practice evaluating on our calculator so we know where the E button is and everything. So if you look at your handy dandy calculator, you'll see E right here above the division sign in blue. Okay? No, well, yes, okay. You'll also see e to the x, which, one second. Oh, yeah. Why did I have two different buttons, though? Yeah, I don't know. Okay, so it doesn't matter. You can put e here and raise it to a power on your own if you want to, or if you use this one over here, it's already saying, hey, you're raising it to a power. So if I do second, e to the x, and I can just type in what my exponent is. All right, now, probably better to use this button because it is the inverse of a natural log when we do logs, so they're inverses of each other. So it's 0.04, and let's go ahead and let's truncate after 4 numbers. Truncate means just cut it off. Typically, that's what you end up doing in calculus. So 0.0497. All right, I can do e to the, and this is not something I would expect you to calculate by hand, okay, because since e is irrational, we won't be as accurate as our calculator can be for us. So 2.0137 e to the 0.91, 0.91 to the 0.484. So the closer that exponent is to 1, it's going to be closer to the actual value of e, of course, 2.7182. And then we've got e to the negative 2. So let's take a look at what happens when we have a negative exponent. All right, a smaller number, so 0.135. What came next? 3. All right, so why are we using e? What's it for? Well, first of all, like I said, it's an irrational number that represents a ratio that you'll use a lot in math and in physical sciences. It's called the natural base because it occurs naturally in math. It happens as you simplify expressions, and you find it naturally in the science world. So let's take a look at graphing them. So we're going to use the same exact patterns that we used for graphing an exponential function. So we still have a horizontal asymptote that exists, and we can find that by looking to see if anything's being added on the outside. If not in this example, we see there is one over here. So this one has a horizontal asymptote at 0 also. Now, E is the base. Excuse me. We have a 3 in front, which is our dilation. So the exponential function, just like every other one, has that point of 0, 1, assuming there's no dilation and hasn't, shifted to the right or left. So we can still use that 0, 1, but because there's a dilation, I'm going to multiply that by 3. So that first point is going to be at 0, 3. Okay? Now, in these, if I have a shift sideways, that's going to take into account a shift on the outside, whatever. What this right here, the point 4, is going to tell me, think about positive and negative. Okay, we talked about that before. If it's a positive, it's going to end up being a exponential growth. It's going up. If there's a negative, like in this one, it's a decay because it flips it over the y-axis. But in something like this, you can just plug in, a couple values for x and get some points and draw your exponential. No big deal. I have my first one, but if you weren't sure, you could have just plugged in 0 yourself for the x and done 3 times e to the 0 power. Any base, no matter if it's an irrational or whatever, any number to a 0 power is 1, so that's just 3 times 1. So that's how I got that 0.03. If you didn't realize, hey, I can just, dilate it up 3. All right, so to get another point, let's just substitute 1 in. So 3e to the 0.4, because 1 times 0.4 is 0.4. Once again, I do not expect you to calculate that by hand. So we can type it in. I mean, you can, by all means. 0.4 is 4 over 10, so you can raise it to the 4th power and take the 10th root. Raise it to the 2nd power, take the 5th root. All right, so that one is going to be at 4.4 and a half-ish, right? So 1 and 4.4 and a half. Okay, if you want to get one more on the left side just to kind of see where it's arcing down, we can raise it to the negative first. So I've got 3 times e. Negative 1 times 0.4 is a negative 0.4. Okay, so 3 e to the negative 0.4. And I get 2. Okay, so that, and a smidge, but 2. All right, so there's my function. So it's the same thing. It's hugging my asymptote. Yay! And then it's shooting up. If you wanted to get another one at 3 just to see what's happening there, you can, of course, do that also. All right, let's take a look at our next graph. So because of the -2 on the outside, that's telling me my horizontal asymptote is shifting down. So I actually would have an x-intercept in this one. Excuse me. Now there is no dilation, so that's nice. My negative exponent is telling me that's going to be a decay, so it's going to go down like this. And this +3 is telling me that's moving to the left 3. So I know, since there's no dilation, that first point is going to be 1 above the asymptote at 0, but because of the shift to the left 3, I can shift it to the left 3. 1, 2, 3. Once again, if you didn't know that, plug in some values and get some points. At least this leads giving me my anchor point, so I know kind of where to start around. So I'm going to plug in -4 because I want to see what's going to go up here because I know it's going up on this side. So if I plug in -4, -4 plus 3, that's going to be a -1. Okay, so I'm doing e to the -0.6 times -1 is positive 0.6. And then make sure the -2 gets moved down. All right, so that gives me negative and a smidge. Okay, so that's right there, negative and a smidge. So I'm gonna keep going a couple to the left because I want to see where it's crossing x. Okay, so I'm going to plug in -5. So -5 plus 3 will give me -2. Okay, so I'm going to do base of -0.6 times -2, and then the -2 on the outside. All right, 1.32. So that one's making it above. Okay, so from there, you can keep going to get a better image, but we know that's going to be something like that. It's not supposed to look like a right angle or an angle, but you got it. Okay. Application problems. And we are going to do more with this when we learn about logs also and kind of combine them. But let's take a look at when E is actually used. It's used when you're compounding interest continuously. So compounding interest is when you get interest on money and then you earn interest on that interest. So it's not just interest on your initial principal, the initial amount you have in your bank account, you're also earning money on the money you earned. Okay, so it's nicer. So here's your formula for compounding interest. PERT, like PERT plus the shampoo. So the P represents the principal. That's the initial amount you have in your account if we're talking savings account. The R is the rate, okay, the rate that you are earning, like 5%, 4%, whatever. And the T is time. And you've got to make sure you read the problem carefully and look at, are they talking years, are they talking days, are they talking months, all that good stuff. So continuously compounding interest is one common real-life application, all right? Well, the bank uses it. So it says you're depositing $1,400, that's your P, in an account that pays 4%, that's your R. Annual interest compounded continuously. What's the balance after 1 year? So that's my T. Now be careful if I said 6 months, T is in terms of year, okay? Because that's an annual interest. So if I said 6 months, you have to do 1/2 up there, right? 6 over 12, because 6 out of 12 months. So we can just do, it's going to be 1,400 e to the 0.04, okay, because 4% change it to a decimal, times 1. Right, so we can type that under a calculator. Oops, I'm opening Internet Explorer and I don't mean to be. Okay, e to the 0.04 times 1 is 0.04. And you get your answer. So there's about $1,457 and 14 cents. You don't earn much interest in the bank, let's be honest. Okay, depositing 800, that's my principal. It pays us 9%, 0.09 after 1 year. So we'll get into some more, a variety of these types of problems later in the unit. So we have 800 e to the 0.9, excuse me, 0.09. So $875.34. All right, and that is all.